Hi, everyone. So it's about 9 o'clock right now. So I wanted to introduce Eiichi Setoyama. He is a scientist here at EGI, and so he will be presenting today. I'm going to hand it off to him, and at the end, we are going to have allow some questions to be asked. So go ahead and write your questions in the chat box on your lower screen. And H will go through some of the questions towards the end. But yes, I'm going to hand it over to H and enjoy.
Okay, thank you, Jennifer, and thank you, for attending this webinar today. Jennifer, I still do not have I cannot share the screen. It's disabled.
Okay, let's see. Okay, try it now.
Yeah, okay. Working, yeah.
Wonderful.
Good. Okay, so I hope you can see the screen in a full screen mode. So I will start by introducing ourselves, and that should give other people to join like a few minutes. So my name is Eiichi Setoyama. I'm a research scientist at EGI, and my expertise or background is micropaleontology. I have two other colleagues listed here. So Sylvain Garel. So Sylvain is a pyrolysis specialist. He's also an organic geochemist. He's based in Paris. And Tulbat Betty, he has a degree. So he finished his PhD in chemical engineering at University of Utah, and he finished a postdoc in data science at EGI a few years ago. So, okay. In this presentation, I'm going to talk about organofacies and its importance and some issues related to identification of organofacies, and then potential solutions that we have employed in the past. And then I will talk about what we can do to improve these workflows in the future. And the use of machine learning is really to help us, and support experts to their life easier. By so the intention of this project or the machine learning models is not to replace us, but to help us to expertise our analysis and interpretation processes. So I will start with the definition of organofacies. So organofacies is a body of rocks, and that contains a distinctive assemblages of organic constituent that can be identified by microscope and also using bulk rock geochemical compositions. And okay, I think I would just stop the video to allow the bandwidth. Okay, and okay, so and there are different types of facies. So organofacies is one. Lithofacies divides rocks based on lithology, and biofacies divide rocks based on fossil content. And we often use the facies concept to delineate different paleo environment. And as you see in the table, organofacies is the same. It's associated with a certain depositional environment. And because the organic matter composition of your sample is mainly controlled by the source of organic matter and the environment of the organic matter through which the organic matter was transported and preserved. So the main uses of organofacies include, the first one is the environment reconstruction. And then the second one is it's a use in petroleum geology. We use organofacies to predict hydrocarbon source potential of your source rocks to understand stratigraphic and geographic variabilities. And then we also use organofacies as an input for modeling of hydrocarbon generation. So organofacies or organic matter have different oil and gas proneness. And as you see in the graph, or not graph, the figure on the right, the timing of expulsion are also different for each organic matter composition or organofacies. So assigning incorrect organofacies to your samples and the intervals you are interested in will have implications, actually a strong implications, for example, for hydrocarbon phase prediction. So it is crucial really to have your organofacies correct. And then there are several different ways to identify organofacies. And so the first one is the visual analysis. So as the definition of organofacies said, you can recognize the organofacies using a microscope. And that is probably the most reliable way to identify organofacies because you are actually looking at organic matters and then identifying them visually, not relying on some kind of proxies I'm going to talk about in the next few methods. The next method is elemental analysis. And here you have the 3 types of kerogens. And kerogens are classified based on elemental composition of organic matter. So you have atomic hydrogen-carbon ratio and atomic oxygen-carbon ratios. But the problem with this analysis is that it's expensive and it's time-consuming. And then the next, probably the most popular method is anhydrous pyrolysis using Lockyer, Hawk, and source rock analyzers. And this method is based on the strong correlation between hydrogen-carbon ratio and hydrogen index, and between oxygen-carbon ratio and the oxygen index. And using these correlations, you have the pseudo-Funk-Levelin diagram that people use. So as you see that you have these boundaries for the classifications of kerogens using hydrogen index and oxygen index from bulk rock anhydrous pyrolysis. Okay. And there are other methods. So for example, people use biomarkers to understand the composition of organic matter and also environment and come up with their own organofacies. And there's another method using XRD, so mineral composition of samples, and also biomarker to come up with organofacies. But again, these requires additional sample analysis, so that this also takes more time and incur more cost. So pyrolysis still remains as the most popular, quick and cost-effective way to identify organofacies of your samples. So although anhydrous pyrolysis analysis is the most popular way to identify organofacies, there are a few issues or problems that is inherent with this method. And the first one is mineral matrix effect. And that leads to the measured hydrogen index value lower than the actual value. I will explain this in the next few slides. And then the second issue is that this is distinguishing oxidized marine organic matter from the mixture of marine and terrestrial organic matter. And there's also another mixture, which is type 1, so laxtrine bacterial organic matter and terrestrial organic matter. So these two issues are kind of major ones, I think, and both have strong implications for source rock potential evaluation. So mineral matrix effect. So what happens is that when you run pyrolysis analysis on bulk rocks, when the samples are clay rich, the clay mineral matrix can retain hydrocarbons, which reduces the S2 values of S2 measurement, and so the hydrogen index values. And another effect is that when the sample has a lot of carbonate component, it increases or this S3 peak, so that your oxygen index value is kind of overestimated. And this effect is more prevalent when the sample has TOC lower than 3%. But there are, I would say, rare cases where your samples have TOC over 3% and up to like 8%, but you still see this mineral matrix effect with your samples. So again, if you're not aware of these problems and if you are not actively looking for these mineral matrix effect, there is a risk of underestimating your source rock potential. And the figure on the right demonstrate how extreme the effect of MME can be. So here you have samples whose measured HI is lower than the original hydrogen index values by 400. And even when you have the measured hydrogen index values lower than the original value by 150, you can imagine how much effect that can have on your source rock evaluation. So this is really important when you are dealing with bulk rock samples and your samples are clay rich. Okay. The second potential issue is the misidentification of organofacies. So the graph on the left shows the data from the North and South Atlantic margins, and you see that quite many of them are plotting between type 2 and type 3 boundaries. And people often say that these are a mixture of type 2 and type 3, which is oil and gas blown. However, when we looked at them visually, actually many of them had altered marine organic matter, which is oil prone. When I said altered, it is either oxidized or eaten by some bacteria, so that hydrogen is lost, but it's still oil prone. We've conducted bulk kinetics and computational kinetics, and then it shows a trend similar to kind of standard preserved marine organic matter. So again, misidentification of organofacies can have strong implications on the timing of generation and expulsion and the type of produced fluids. So again, it is crucial to have your organofacies correct. So now I've described these two potential issues related to anhydrous pyrolysis. And in the past, we did a project on the Atlantic margins, and then we adopted this workflow using pyrolysis, and which is published in the journal. So, but in the next 5 or 6 slides, I'm going to describe how this workflow works and what. Okay, but I will start with what pyrolysis is. So these are the project we conducted before and applied this workflow. So, okay, I will start with the pyrolysis. So pyrolysis is a study of the total assemblages of particulate organic matter in your sample after removing the sediment matrix. And the difference of pyrolysis and the organic petrography or petrology is pyrolysis allows you to see organic matters in kind of 3D. So you are not only looking at the slice of organic matter, but you are actually looking at the entire body, a whole body of organic matter. And that helps when you identify organic matter. And also you concentrate all these organic matter. So you can do point counting. And then in this case, Sylvan does more than 2,000 point counting, which kind of gives you a good statistical reliability for the identification of organic matter and then organofacies. So on the left, you see the standard kind of kerogen classification. So we have type 1, type 2, type 3, and type 4. And then on the right, revised end member is based on the observation of pyrolysis from both onshore and offshore Atlantic margins. And on the right, further right, you see the translation of end member to kind of kerogen classification. And you see that the hydrogen index value range kind of overlaps with between, for example, standard type 2. Standard type 2 is okay, but then when you have mixed type 2 and type 3, the hydrogen index value range overlaps with altered type 2. So this is very difficult if you do not know the existence or the presence of altered type 2 in your basin. So it is, I'd recommend if you have chance just to do some visual kerogen analysis, either pyrolysis or organic petrology to make sure that you know what kind of organic matters you have in your basin. Then now we have the classification of organic matter. Then we do identify the samples and intervals affected by the mineral matrix effect based on the difference between the expected HI values based on organofacies or pyrolysis, and then the measured hydrogen index values. So when there is a huge difference between the measured and actual expected values, then we say that samples are affected by the mineral matrix effect, and they need the hydrogen index values correction. And then, so for the standard mineral matrix effect, we use the published equations and correction chart to correct their hydrogen index values based on their organic matter composition or organofacies. But Sylvan recommends that when you have strong MME, so those samples with TOC over 3%, but still affected by mineral matrix effect, he recommends that you should have kind of basin-specific equations and chart to correct their hydrogen index values. But to do this, the selection of samples for pyrolysis is very important because you do not want to miss the intervals or samples affected by the mineral matrix effect. And in our case, to make sure that we cover all the organofacies and also the intervals of possibly affected by the mineral matrix effect, we looked at all the available information and data, including sedimentology, paleontology, to identify samples whose hydrogen index is not in line with its depositional environment. Okay, so I talked about the two issues, so mineral matrix effect, organic matter mixture or not. So the identification of organofacies, they both have strong implications on your source rock potential evaluation. And I hope that I demonstrated that pyrolysis can be used to solve these problems if you have access to the expert. And these are the examples of before and after organic matter reclassification and mineral matrix effect correction on hydrogen index values. So on the left, you have the source rock kind of evaluation using the standard Kelvin classification without mineral matrix effect correction. On the right, you have the source rock evaluation using the refined organofacies classification with hydrogen index values corrected for the mineral matrix effect. Okay, so on the top, we have an example from the alluvium offshore Guyana, Suriname. And as you see that after organofasci, organic matter reclassification and MME correction, the potential, generation potential of the source rock increased. And this is not, this is due to the mineral matrix effect correction and organofacies reclassification, because based on the, if you are just using that hydrogen index values from the lab, and most of your organic matter would be mixed type 2 and type 3, but the pyrolysis observation showed us that they are actually marine, altered marine organic matter, and they are more oil prone. And then we have the second example is from the southern South Atlantic. It is a Kimmeridgian source rock, and it again shows that before the mineral matrix effect correction and organic matter reclassification, I would say half of the organic matter is heterogeneous input, so it's a mixture of type 2 and type 3. But again, the visual identification showed us that most of the organic matter is actually the altered marine, and so that it is far more oil prone than it was originally thought. So, but of course, there are other, there are stratigraphic intervals and basins which do not suffer from the mineral matrix effect, and the standard classification of Kelvin works well. But in these examples, and also other examples we saw in both offshore and offshore South Atlantic margins, we've seen the cases where that you really need to correct the HI values for mineral matrix effect, and you need a reclassification of organofacies to really understand the source rock characteristics of the basins on the margins. So, so now we have some experience with our pyrolysis workflow. We also accumulated some data, and the workflow works well. And at least we know that the sponsors were happy with the results of the project. However, the workflow is not perfect. For example, the selection of samples and then performing pyrolysis takes time, and it also incur more cost. And I think the largest problem is that there are not many pyrolysis specialists. So access to the expertise is limited. So after these two projects, we decided to use what we have accumulated, so the data-wise, and then also the experience, and then to use them to speed up the entire workflow by building machine learning models that can help us to identify samples and intervals may be affected by the mineral matrix effect, and also assign or predict the organofacies using our refined classification. And again, I'm not saying that you should use these classifications or predictions, but you can use them to test your own interpretation of organofacies. And if there are differences between your interpretation and prediction by the machine learning models, then you might want to pay more attention and look at these samples and make sure that your interpretation is correct. So that is the intention of these models. So for the models built so far, we have gathered data from offshore and offshore Atlantic margins, and they come from the EGI reports and also the reports and papers publicly available. But they have to include these required data types. So and these are rock types, rock color, TOC, HI, Tmax. Tmax is for maturation or maturity, and then the information if the environment was terrestrial, marine, or marginal marine, and of course we need a data on pyrolysis so that we can determine if there is a mineral matrix effect or not, and then also to determine the organofacies for each sample. Okay, and this is the kind of summary of data distribution we used for building these models. So there are a total of 1,005 samples. And regarding mineral matrix effect and no mineral matrix effect, there is a good distribution. Unfortunately, with regard to organofacies types, I cannot say that there is an equal distribution for each organofacies types. But yeah, we have to work with what we have. I cannot change this, but we have, after this analysis, we have increased the data set size, and we have more than 2,000 samples now. So there is a little better distribution of samples for each organofacies types. But for this exercise, I only used the data from South Atlantic and North Atlantic margins. And the graph on the left kind of shows nicely that organofacies identification is based on the pyrolysis here. And then you see that these cross, which are affected mineral matrix effect, even they are dominated by the standard marine organic matter, which is type 2, their measured hydrogen index values are much lower than expected. So these are the things you want to look for if you are trying to identify samples with mineral matrix effect. So this is something you can do. So you plot HI against TOC, and then use paleo environment to see that disagreement between the expected hydrogen index values and then the measured hydrogen index values, and then select samples for the further analysis. Okay, so here are the results for the mineral matrix MME prediction using a model. So we only use the samples which are immature, so 1,005 samples, and we used 75% of the data for training and then 25% for testing. And input attributes include rock type, rock color, TOC, and hydrogen index values. So very simple. And then the output is the prediction of whether a sample is affected by the mineral matrix effect or not. And the result, the accuracy of this model is 90.4. So I think this is pretty good, especially when the input values are so, so few. And I haven't done any hyperparameter tuning. I didn't use any ensemble method to improve the prediction accuracy so far. So this is just, the algorithm coming kind of out of the box without any tuning. And here are the other results. So when you add oxygen index, somehow the accuracy decreases whatever you do. I tried few other models, but then oxygen index values always lowers the accuracy of the prediction. When you add terrestrial marine or marginal marine added, actually doesn't really affect the accuracy. You still get the same accuracy, and it's the same with oxygenation. So for some, these kind of environmental attributes did not help with the prediction of mineral matrix effect, except for the displaced sediment. So displaced sediment is identified by microfossil content. So when you see, for example, you have that deep water assemblages, but you see these species, taxa, which are characteristics of the shallower environment, then you can detect that, okay, some of the sediments were reworked or transported from different environment, and that affects your organic matter because you have more terrestrial organic matters in the shallower environment, and then maybe you have more oxygenated environment in the shallow environment when you have anoxic or oxygen depleted environment in the deep water environment. So the introduction of these organic matter from different environment is important. And then it seems that it helps to increase the accuracy of the model a little bit. And when we use all the attributes, including so all of them, displaced sediment, oxygenation, and then the terrestrial marine, marginal marine information, the accuracy increases even further. However, to keep this model simple and then make it usable for any situations, I think we'd better stick with these 4 input values or attributes because the accuracy is already pretty high. So if we are going to, when we are going to publish this study, I think we just stick with these 4 attributes. Okay. So there is so the detection of mineral matrix effect, we had a good prediction accuracy. However, when we try to predict if there is a strong mineral matrix effect, the accuracy decreased by 3%, or it's actually 4%. And so the detection, again, if there is MME or not, the accuracy remains the same as you see in the number of the samples for no mineral matrix effect are the same, and then there is only one change in kind of misidentification. So the decrease in accuracy is due to the misidentification of samples with strong mineral matrix effect. For some reason, when you add strong mineral matrix effects, the model says that some samples which are actually affected by strong mineral matrix effect are not affected by mineral matrix effect. And I think this is due to the TOC values we have. So I think tuning the input values, especially for TOC, might help increase the accuracy later. So okay, here are the results for the model to predict organofacies of samples. So for this model, we only use the samples without mineral matrix effect. But we used more input values for this model because I will show you later. But the prediction of organofacies, these environment related attributes are very important. So the accuracy of the prediction with this model is 90.6, which is good. However, because the sample size, the data set size is a little small, and then when we randomly split the data set for training and testing, unfortunately, we had only one sample representing an altered type 1. Yeah, that's unfortunate. But I think when we run the model or not run the model, build the model with a larger data set, I believe that we will have more samples representing each organofacies. So I think that this won't be a problem. And here are the other results with different combination of input values. So with oxygen index value added, unlike the detection of mineral matrix effect, it didn't really affect the prediction accuracy. So the accuracy remains the same. When you only use the log type, log color, TOC, and HI, accuracy is much lower. So it shows that having that input attributes related to the PIRA environment is very important. And if you remove these oxygenation and displaced sediment input attributes, again, that the accuracy decreases a little lower. It's not a drastic change, but there's a small change in the accuracy. So I think when you have these attributes, I think definitely you want to use them. And the one environmental input you definitely want to keep is that terrestrial or marine or marginal marine information. And without it, the prediction accuracy is again much lower than 90.6. So these are the results of the models we have so far. And as you see that there are the rooms that we can improve, and the spaces, rooms we can improve the models. And the first one is that we definitely need to increase the data set size. So currently for this exercise, the data set included only 1,005 samples, but now we expanded the geographic coverage of the data set. So now we have more than 2,000 samples. So hopefully with this larger data set, the accuracy of the models will increase, and we will have more samples representing each organophagy types. I don't, for the detection of mineral matrix effect, I don't think, I think we already have a good model. So I think, well, it probably increases the prediction of mineral matrix effect, but I think the effect maybe not as much as for that organofacies detection. And then we have all these other things we can do. For example, we can modify input attributes. So log type and log classification, I kept it very simple. For log type, I only had clay stones, and then another group is shale, mudstone, siltstone, and then everything, and then sandstone is another is a separate group, and then I had everything carbonate, and then or calcareous, and then everything biosiliceous. And I see that, and as we all know, that there are log types which are clay rich as well. For example, marlstones milestone is right now is included in everything carbonate, but we know that there are some milestone samples affected by mineral matrix effect. So adding this extra category for milestone might improve the improve the model's performance. And then color classification is another thing. People are very creative and inventive. People use different names for the same color, and so having this classification is a little tricky. Right now, I have less than 10 right now. I think I have like 8 categories for colors, but maybe I can reduce that, or maybe if needed, add a few more categories to increase the accuracy of the models. And then although we collected the data like microfossil count and the sedimentary structures, we didn't use that for this exercise, but maybe using these kind of raw data from the report might help us to improve the accuracies. But of course, these informations are not always available. So there's a pros and cons of including these additional kind of raw data as input attributes. So I haven't done any hyperparameter tuning, and we only really used random forest algorithms for this exercise and didn't use ensemble methods. I tried a few other like native Bayes and kind of native Bayes I used, but yeah, the accuracy was much lower. So but trying other different algorithms and an ensemble method, maybe we can find a better way. We can build a better model for MME detection and organofacies identification. And then the last step for this study is really to identify the samples with MME and then correct the hydrogen index values, and then identify the organofacies based on the corrected hydrogen index values. And these are for the future studies. These are the suggestions we had from people. So the requests were to include log data and then identify samples with drilling mud contamination and identify samples with an FID saturation. Yeah, this would be nice to have as capabilities, but these are for the future study right now. So this is the last slide of this presentation. So so we looked at this definition of organofacies and then the importance of having the correct organofacies. And then we talked about the potential issues of anhydrous pyrolysis, which is the most popular method to identify organofacies, especially in the source rock screening step. And then we looked at the possible solutions that we have used at EGI. So we looked at the pyrolysis approach and the machine learning approach. And machine learning approach, even though our models are very simple and basic, we already have a good accuracy to do the job. And then we looked at the next steps for the future. So this is the last slide. So I will probably stop sharing the screen.